What we're doing today is, Rick and Ray and I and others have been doing pulsars for a while, and um, Rick had asked that we'd kind of do a set of training sessions on how we do it, so that it doesn't just depend on me or even the computer that I bring down. That anybody can basically go down and do it. So, what I'm going to be talking about today is just the mission planning part, how we go about deciding which pulsars to do. So, this is more how we do it. I'm not going to spend too much time about what we do. I mean, I'm not going to spend too much time about what a pulsar is. More of the focus is going to be on how we detect pulsars at Haswell. I'm still getting warmed up here. I'm going to cover a few fundamentals of pulsar astronomy. Then I'm going to, and we'll talk about the ATNF, that's the database, all the pulsars that we use, a couple of tools, Murmur and Stellarium. And I'll talk about what goes through my mind and how we decide which pulsars to work when we're down there trying to fish for pulsars. And then we'll do a little bit about some of the parameters for data collection. Um, a follow-on session after this will probably be focused on the B210, the parameters that we set for the B210, and we'll probably run that from Rick's house where we can do live demos with that. If you want to know more about what a pulsar is, I recommend this Handbook of Pulsar Astronomy by Duncan Lorimer and Kramer. It's several of us have this book, but it really lays out all the foundations of pulsar astronomy. So I don't know why things are different. Whenever I bring up Zoom, my computer goes different. So this, you might have seen this before. This, you know, the atmosphere is transparent to frequencies from roughly 5 megahertz to 30 gigahertz. And with the dish and Haswell, we can do um, a few hundred gigahertz or a few hundred megahertz up to maybe 8 or 10 gigahertz. The whole focus on this slide, I want to talk about RFI. Um, Ray and I have spent more time analyzing noise and chasing RFI than we have spent on pulsars. And so it's really important to be aware that there's external sources of RFI that can just destroy the pulsar signal. So the pulsar signals are very weak, and we need to get rid of all the RFI we can. So the sun is a big source. You don't want to be detecting too near the sun. FM broadcast radio, all the mobile comms. So we pick up. There can be construction crews out on the highway near Haswell, and we can pick up their mobile comms. There's navigation radar, air traffic control, some of the LEO satellites, ham radio, because sometimes I use the ham radio bands. They're usually quiet, but there's ham radio traffic there. We have a cell tower that's near Haswell at 409. So there's all those things. And then everything that we bring, stuff you got in your pocket, every single computer screen, every single computer, everything can be suspect down there, even cables, all the Wi-Fi, the Bluetooth, cells, all those things can add to the RFI. Um, Even the lights and utilities, equipment up in the pedestal. So last year, the team did a great amount of work to improve all the grounding and bonding in the new control room, and that really helped us a lot, and having new coax help. So anyway, just be aware of RFI, either external or just coming from the shack itself. Um, and this is a standard diagram of some of the radio sources showing the sun up at the top. and the active sun. Then in the middle are some of the supernova remnants. The scale on the left is in Janskis, and a Jansky is defined there as 10 to the minus 26 watts per square meter per hertz. Um, but the takeaway from this chart is, oh, most of the pulsars are millijanskis, so they're not even on this chart. Pulsars are down in the millijansky range, and also pulsars are broadband emitters. And so we're not using narrow band filters. We use get as wide a band as we can to detect them. Um, so there's really only two things we can observe on a pulsar. One is its period, and the other is the rate of change of the period. That's also called the period derivative. And so these two properties can be combined, and they call it the P dot um, chart because and it's a log chart. Along the bottom is on the x-axis is the spin period in seconds, and the y-axis is the period derivative. That'd be the rate of change, or it's also called the spin down rate. These pulsars are gradually slowing down, but there's different lines on the chart, and it shows at least three different things, including the characteristic age of the pulsar. And I put a note in there, the characteristic age is a calculated or a derived age. It's not the true age. For the Crab pulsar, we know its true age because it was documented in 1054 when the supernova went. So we know its age. Most of the other pulsars we don't. So we estimate their age from this, and that's on the chart. We can also estimate the minimum magnetic field strength on the surface of the pulsar from the spin down rate. And so that's called, we'll see it later on ATNF, it's called the B surface magnitude. And then the spin down luminosity shows up also. The kite-shaped diagram is where we've detected pulsars, basically in the middle. There's roughly 3,000, well, there's more than 3,000 pulsars have been discovered. We do not discover any new ones. We're always trying to detect known ones. And so in the middle is where we're operating. Those are called radio pulsars. There's also X-ray pulsars and gamma ray pulsars, but we focus on the radio pulsars in the middle. But we've also detected one MSP. And MSP is the millisecond pulsars. And those are very interesting. We'll talk more about, but we detected one of those. So the range of period that we've detected the fastest one was 5 milliseconds, and the slowest one was 1.9 seconds. So those are the range of pulsars that we've detected, and it's just an indication there of what part of the total population we've been looking at. This schematic kind of outlines the whole detection procedure. You start with this neutron star. There on the left, you have a neutron star, rapidly spinning neutron star. That's it's the collapsed core from a star that went supernova, and it formed into a neutron star, which is just one stop from a black hole. If it would have been a little bit more massive of a star, then it would have continued on to a black hole. So neutron stars are exotic. They are just, like I said, one step above a black hole. They're very lots of interesting properties that are just slowly being discovered. So as this star is rotating, and it's small, it might be just 5 or 6 miles in diameter. They're small, very compact. They rotate quickly. There's a very strong magnetic field on the surface, and they are putting out this radio beam that we see. So we see this radio beam go flashing by as it sweeps by, just kind of like a lighthouse. That's the pulse that we can detect. And so you connect a receiver to your telescope. In this case, we use the USRP B210. And then we use a program called Presto which is the same program used by the professionals. So if we detect a pulsar, there shouldn't be a whole lot of doubt about it because we're using the reliable software. So we do something called dedispersion to straighten up the signal. And then in the upper right, we produce this pulse profile. It's a statistical average. It's not a individual pulse. It's the statistical average of the pulses. And we've been happy so far just to get to that, to get to the pulse profile. With Rick's new clock, we might be able to do better. We could actually now compute the TOA. The TOA is the time of arrival. And so that's shown there. It's time of arrival is an absolute value, but it tells you when each pulse arrives. And then you can do some interesting science from that. So we'll talk more about the TOA. Um, so um, coordinate, once you decide you're going to do some pulsars, then coordinate with Roger and Ray which feed horn you want. And usually it's best to get the installation done ahead of time. Otherwise, you spend a good part of the day just doing the installation. We do not have calibration procedures in place. So bench testing helps. If you do bench testing ahead of time, then you know that the LNA and everything is working um, on the feed. I guess just in terms of terminology, I think one gigahertz is kind of the dividing line. If you're below one, like we have 408, we have an antenna. So below one, we call it antenna. Above 1 megahertz, above 1 gigahertz, then I think it's often called you're in the microwave realm, and it's called feed horn. Uh, Either way, we use the B210 with GNU radio, and we bring the RF, the analog RF, down the coax feed line from the hub. So many of you are probably aware that there's a newer capability of actually doing the data collection at the hub and then bringing the data down in a file on fiber. So we're not doing that yet. We're still doing just the coax feed line in the control room. When we run GNU radio, it generates a filter bank for post-processing. And what I've done before is I would take the DSES Pulsar computer down to Haswell and plug it all in with the B210. And I would do both steps together on the same computer. I would do the data collection and the post-processing all scripted, and it all takes place on one computer. And it might look like one process, but it's really two. And what we're talking about doing now, what Rick and others are advocating is, well, we can divide that into two different steps. The first step being, well, we do the data collection down there. We still have to do data collection, but we don't have to have this computer down there. We can do it on a Raspberry Pi 5. So we can do data collection down there. And now that we have fiber, we can push the data out to anybody that wants to post-process it. We can kind of do a two-step thing, data collection. And then once we have this filter bank file, then that can be FTP'd to others who want to do the post-processing. Post-processing sometimes can be a few minutes, and sometimes it takes a few hours. If the automatic process, if it works quickly. If it doesn't, you're doing manual, and it can be a while. A filter bank file is, so some of you might be familiar with the INQ file where you're collecting the raw data. Filter bank is much more compact than INQ. It's kind of like it says, it's a bank of channelized data. So the data, you can think of the data has been converted into frequency channels. Each channel has a certain width, and then you stack all these channels up, and you have a filter bank to cover your whole bandwidth that you're working that day. Something that's very nice is system one is how we control the dish. And we cannot control the dish remotely. We always have to have two people on site. But system one already has a table. It's a radio source table. It has all the pulsars that we could ever possibly collect. They're all in the epic is called J2000. So the easy part is running the dish. You go down there, fire it up, select um, your desired pulsar from the system one table, and start tracking. And then once you start tracking, then you would start doing the data collection with the B210. And this is what our configuration looks like. We used to have a GPS clock. Now we have a rubidium clock for synchronization. Um, and like I said, for data collection, we can use the Raspberry Pi 5. And we have this B210. I've listed 3 feed horns that we've used. We've used the 408 megahertz. And the important thing for pulsars is you want to know how wide of a filter there is on there. So that one has a 90 megahertz filter, meaning we're centered at 408 when we go plus or minus 45 megahertz, up or down. And then we've used the older 1296 feed that was also used for EME. We've used that successfully for many pulsars. And we've used the hydrogen feed, the 1420 hydrogen feed we've used often for pulsars. We also have a 437 feed that we'd used. So our current campaign, what we've been thinking of doing is in fact, it's already up there, I guess, is using the 408 feed. So the 408 feed it's a dual dipole antenna. And here in the middle of the page is the software that we use. We use Murmur and Stellarium to plan the observations, and we use the ATNF database. That's what I'm going to be talking about today. It's just those first 2 lines. So the next time we meet, we'll talk about various spectrum analyzers and how to use the B210 with GNU radio, how to look for RFI and some of those things. And then for those that are interested later, we'll do the actual post-processing with Presto. So when I'm trying to decide, all right, so we're planning a pulsar trip, I'm trying to think, well, what do we want to do? This is the DSES Pulsar catalog. This is on DSES website under the science projects under Pulsars. So this catalog is there, along with most of the profiles from these pulsars. So we can think, well, do we want to go do another new one, or is there something, an existing one we want to look at? So these are the pulsars. A comment sometimes, or most of the pulsars that we see start with a B. And then you'll see some of them have a J. All of them, the numbers are, the first are the right ascension, and then the second part is plus or minus S the declination. The B means it's 1950 epic. The first pulsar was discovered 1967 or something like that, and those were given epic of 1950. Pulsars like number 3 and 4 here that start with J, what it means is they were discovered after the year 2000 and they only have a J designation. They don't have the B designator. And that's because after 50 years, the pulsar in the sky has drifted a little bit. The right ascension and declination have changed a few degrees. So every 50 years they update those. So that's why you're always going to see a lot of them have 2 names. But then I just listed when it was first detected. Several of these we've detected several times. Then I list the period. As I said, we caught 1 millisecond pulsar, which is this one right here, number 4, 5 milliseconds. That was the fastest one we've ever done. Then I list the pulse width is an important measure. So the width of the pulse is measured 3 dB down from the peak. 3 dB is also called the W50. It's the half width, half max of this pulse. So that's the width in milliseconds. dm is this dispersion measure. Think of the dispersion measure as the column of electrons between your telescope and the pulsar. So there's this column of electrons that the radio beam has to come through, and if it's thicker, the dispersion measure is higher, and that just means that the the radio beam gets scattered more. So in a rough sense, dispersion measure also gives you an indication of distance, but they're not the same. The dispersion measure can be higher for something that might be closer, but it's kind of an indicator that, if dispersion measure is high, then it's further away. I list the S400 or S1400. That's the flux in millijanskis, and that's also an indication of which feed horn we used or which antenna we used to collect that. And then how much time. And the integration time is how much time we collected data for. And that helps us when we're planning future observations to get an idea, well, how long that one took, and this one's comparable, how long this one might take. So,
Dan?
yeah,
Yeah, go back to the dispersion measure for a moment. So that's its dispersion over time, correct? So it's basically smeared over time,
it's smeared over frequency.
over frequency. Okay.
The What happens is the electrons um, distort the signal and they affect the high frequencies more than the lower frequencies. So when you first look at the pulse, um, it's not vertical. The pulse is kind of standing, it's drifted. Part of it, the top's drifted, and so it looks it's not straight. And so you have to straighten it up. The dispersion measure allows you to straighten up the pulse. And that's also related to the channel width because you want your channel width to accommodate a pulse that's been dispersed and it's not straight. If your channel width is too narrow, then it spills over to the next channel, and so you get some channel distortion in your FFT.
Okay, thanks.
Yep. So I keep this in the back of my mind, and then just some frontiers to explore. Basically, we have improved timing with the rubidium clock. I think we have a better time source than we did with the GPS clock, and that'll stabilize the B210 and also help us do TOA. We also have better sensitivity. Last year, the team did extensive grounding and bonding and installed that new coax feed line, and we got much better results last August when we were down there. So the question is, if we're planning a mission for pulsars, what can we detect? Well, first of all, I listed the millisecond pulsars. Millisecond pulsars are old, they're stable, many of them are binary. We have detected 1 millisecond pulsar, and it's J0437-4715, and it's binary. So if you've read any of the literature, you might have seen some science announcements now and then that the scientists are always on the hunt for gravitational waves, and there's various methods to detect gravitational waves depending on the frequency they're looking at. So they're using LIGO and some of the laser interferometers, but they're also using they call it pulsar timing arrays. So these are big dishes like at Green Bank or Parks in Australia. The pulsar timing array is not an array of telescopes, but rather it's an array of pulsars scattered across the sky that they constantly monitor these pulsars for changes in their period. They correlate those changes across various the other pulsars to see if a gravitational wave might have gone by. So they're doing it's a stochastic method, but they use millisecond pulsars because they're stable. The newer pulsars are not as stable. Their rate changes quicker, so they like to use these that are nice and stable. Anyway, I think we could realistically collect some more millisecond pulsars. Um, so those would be faster ones. At the other extreme are slower ones. The slowest one we've ever detected was 1.88 seconds. I think the slowest pulsar at ATNF is around 3 seconds. A problem is the tool that we use, Presto, to detect pulsars it was designed to find new millisecond pulsars. So it's designed to detect new millisecond pulsars, and it doesn't do as good on the slow ones. It's a statistical algorithm. It doesn't do as good. In fact, we have a couple of cases where Presto did not detect a slow pulsar. I used the alternate algorithm. It's a time series algorithm called Riptide. So I've used Riptide to detect slow pulsars. So that's an option. Um, some other things to think about is, well, we can always try fainter pulsars. The fainter you go, the more there are. So we've detected 25 pulsars, and there's over 3,000. We have not even detected 1% of the pulsars that are out there. Most of them are much weaker, but the weakest one we've detected was at 1,400 megahertz. B2111 plus 46 has a flux of 19 millijanskis. And that 19 millijansky is an ATNF value. That's not a value that we were able to derive, but so we can always try fainter ones. Um, we can do younger or older ones. I talked about the age of pulsars. Um, Most of the pulsars we've detected are around 1 million years old. The crab, which we've detected, and it's a very interesting pulsar. We know it's 1,000 years old. The millisecond pulsars tend to be around 1 billion years old. And I'll show you here in a little bit how you can figure out which, if there's a pulsar of interest, well, how do you even know ahead of time what it might be? Then we could look for closer pulsars. The closest one that we have is 0.16 kiloparsecs. And if you convert that to light years, that's 490 light years. So that's fairly close. The furthest way that we've detected is 7.0 kiloparsecs. We've detected a pulsar there. So 7 kiloparsecs is the same as 22,800 light years, which is most of the way to the center of the Milky Way. So I think it's around 8 kiloparsecs to the center of the Milky Way. So we've gotten most of the way to, we found a pulsar there most of the way to the center, which I thought, well, that's cool. And just for comparison, this is the range of the dispersion measure that we've detected. 2.6 was the closest one, the weakest, no, I mean the closest. And then the one with the highest dispersion measure was 400, the dispersion measure is 478. Then if you don't want to go looking for new ones to add to the collection, by the way, we have compared with other sites, other amateur sites. Some have collected 30 or 40 or 50. A couple of them, I think Wolfgang's collected 200. So various amateurs have collected other good amounts of pulsars. Um, if you don't want to go, try and detect a new one, which to me has been frustrating because Ray and I have gone down there many times and come back empty-handed. There's been so many problems. We go down there with great dreams of collecting 3 or 4 new ones in an afternoon and come back with nothing. So sometimes you might want to do a repeat observation on the same pulsar. And that would be if you want to do scintillation studies of the interstellar material. So the interstellar material, meaning the gas and dust, interferes with the radio waves coming, and it's in a repeatable pattern. B0329 plus 54 is a reference pulsar. It scintillates. Sometimes you set up, you want to observe it first, make sure everything's working, and you barely detect it. You think, well, something's wrong here. But you got to remember, it scintillates on the scale of 10 to 30 minutes. So it's not like a twinkling star that's real quick. These are like 10 to 30 minutes, it will fade in and out. Also, 2020 plus 28 does that. So There's some interesting studies to do on scintillation. Last August, we did a great study on the crab. We took 6 hours of data on the crab pulsar, and it actually has three different kinds of pulses. Besides the main pulse, it has a interpulse, which is a smaller pulse. It's 140 degrees off of the main one. And then it has these random giant pulses, which are more intense, but just random, that it throws out that we also detected. A third thing we can do is start exploring the astrophysical causes of timing residuals. So think of the pulse time of arrival. That's the absolute time arrival of a pulse. Then you form a residual. A residual is the observed time of arrival, and you subtract from that the modeled time of arrival. So when you model it, you model every single thing, every single cause of timing. It could be any, if you know what your clock offset is, any instrument effects, the pulsar spin down, you account for everything you possibly can, and they're still residual. And so you can start studying the residuals and explore further causes of those. Those are also helpful on the people doing the gravitational wave detection. So I have tried to do residuals here at DSES. I have not succeeded at it. I have done it with Green Bank, but if we're going to do it here with the rubidium clock, you'll need the new version of Presto. So I'm running Presto 4.0. I just haven't upgraded yet. The so there's a routine there that'll get the TOA for you. Does all the hairy calculations for you. It's just called getTOAs.py. You run it with Python, and it's broken. It's seriously broken right now. It's because NumPy changed. So that's the problem with Python. Sometimes they change the library and it hoses your code. So Presto 5 fixes that, fixes all the NumPy lib errors, but that's something, we can get to at a later date.
Dan, is there a charge for the Presto software?
No, no, it's on GitHub.
Okay.
So it only runs on Linux. There's not a Windows version. It just runs on Linux. But when we do the post-processing class, we'll talk about Presto and how to get it and how to install it. Rick put together a nice document that kind of summarized all of my notes of all the ins and outs. You need a ton of libraries, and although the new version 5 is easier to install. But yeah, all the software that I'll be talking about, it's all free. Most of it's on GitHub. So where do we start? So we don't have a calibration procedure. Although, well, I should say with the 1420 feed, Ray's installed a noise diode in it, and we can control that from the control room. So we can do calibration. And in fact, we've tried, but we don't actually have a good procedure for doing that yet. So lacking a good calibration approach, we always just do a 10-minute collection on our standard pulsar, 0329 plus 54. It's circumpolar, so it's always up. It's always available and up. And what we do is just compare previous collections at the same frequency just to get an idea that everything's working. So that's kind of our starting point. And many of you have seen when we're down there running this, once I get the B210 set up, I'll run a collection, and then right away it produces a plot just like you see here. That's because I have the post-processing scripted together with the collection. And what we're talking about now is, well, we can break those into two pieces easily. So I'm going to go ahead and finish this presentation, and then I'm going to come back and do some demos of this software. And the first one is Murmur. So this is produced by Ham in Italy. And basically he takes the ATNF database, so that's the Australia Telescope National Facility, They have a database of all pulsars, and they keep it fairly current, up to date. So it has all the values you could ever want in one place, and there's various ways to interface with their database. One of them is use Murmur. And for Murmur, you set your location. For example, here you can see that this is set for Plishner with the latitude and longitude down there at Haswell. And then we set the dish parameters. It's 18.3 meters. We estimate some of these line losses and values. This is the integration time in seconds. So I just set it for an hour. And the integration bandwidth, it depends. Depends on how much clean bandwidth you can find here. I just said do 20 megahertz. And you'll see when I do the demo, you hit this calculate button. It gives you the standard noise figures and things, but it also tells you about the pulsars that are above horizon at your location, and that they all they exceed a signal to noise ratio of 10. You can set that to whatever you want. And they're ordered, you can change how you have them ordered. Here they're ordered by signal to noise. So fortunately for us, our reference pulsar, plus 54, that's circumpolar, is also the brightest pulsar in the northern hemisphere. So we start there. And some of these values are going to be values we need for the parameters for post-processing. So I highlighted those, like the W50 is the pulse width at 50% of the peak. Oh, so it says barycentric period. Barycentric period is the period of the pulsar as measured at the barycenter. That's the mass center of the solar system. Well, the mass center of the solar system is not on Earth. It's much closer to the sun. All of the calculations that we do and everything we do with Presto and Tempo, we are calculating the topocentric period. The topocentric period is the period measured at the telescope here on the surface of the Earth. It's slightly different. It's not enough different to worry about, but slightly different than the barycentric period. Then they also list the dispersion measure. So these are the values that are here are not calculated. These are values from ATNF. It gives you the flux values, the distance, its age. So you look here if you're trying to think, well, is this pulsar interesting? And then it gives you the maximum channel bandwidth, assuming no D-dispersion. So this tells you, kind of gives you a hint where to set your channel width, and then the expected signal to noise ratio. And this number highly depends on the bandwidth. The wider bandwidth, the better signal noise, and then the time. The more time, the better that is. So you can play with those numbers. So we'll see more of that when we do a demo. So yeah, for the demo, we'll look at the ATNF Pulsar catalog. If you're interested in doing the post-processing and running Presto, you'll also want to download the catalog itself, and I'll show you how to do that. It's a relatively small database, and they have some tools, and I use those tools to generate a parameter file, and that parameter file feeds Presto, and that really helps eliminate a lot of the guesswork instead of doing it manually. We'll look at Murmur, and then we'll look at Stellarium. I use Stellarium to verify the track in the sky before I go down to Haswell, because there's been several times Ray and I'd go down there. I'd be all excited. We were tracking a pulsar, trying to do a 4-hour collection, and halfway in, System 1 stops the dish with an alert saying, you're in the sun zone. You're too close to the sun. It stops tracking. So I like to make sure that the sun is not going to be interfering with the track. Number one, if we get too close to it, it's too much RFI at the lower frequencies. Number two, System 1 won't work near the sun anyway. And I also like to get an idea, what does the track look like during the daytime in the sky, so I can glance over at the dish and realize, yeah, it's pointing in the right side of the sky. It's pointing in the right place. For the dish location, for some of the software packages, you want accurate location, and Rick has provided this from his new software and new tools. So it's the latitude and longitude at the feed horn. What I used to use, I just used something off of Google Earth or something approximate, but this is right at the feed horn, the GPS lat long. So use these values if you're trying to find something for the location. Comparison websites. So I do compare with other websites. First of all, our own website has the Pulsar catalog, and it has almost all the pulsars that we've detected. So you can go there and see previous observation reports and previous profiles. K5SO is, oh, I forgot his name. What's his name, Bill?
It's Martin, Joe Martin.
Yeah, Joe Martin. So he's down in New Mexico. He's retired his dish, but he had a 30-foot dish in his backyard in New Mexico, and he collected many, many pulsars. And in fact, he is how we got started because Rich and Ray met him at a conference in New Mexico, and I think they went to his place. And so Joe Martin set up Rich's computer with Presto. So not Presto, I mean the GNU radio. So we use a modified version of GNU radio from K5SO. But his website is, even though he's not actively doing astronomy, his website shows all of his detections. I found it very helpful to go to see, well, how long did it take him to do this collection, just so we get ballpark ideas. The same thing, there's this other one in Italy, OE5JFL. He has a number of pulsars he's detected. I think he has a 7-meter dish. The neutron star group is not as active. That's where we used to post our results. There would be different groups in the world and say, yeah, we've collected 5 or 10 or 20. And so Rich Russell would send him our table now and then, but there's a lot of good information there. The EPN Pulsar Profiles. EPN is the European Pulsar Network. It's run by a volunteer there at Jordrell Bank. The website is not always up, but when it is, I like to go there because they show the profiles for any of the pulsars we would detect at almost any frequency. So you get a good idea of which frequencies might work. And then the Green Bank 20 meter. So if you're in Sarah, you can go use the Green Bank for short collections. They don't like you to do a long collection with a 20 meter because that'd burn up Sarah's account, but you can use it for short pulsar collections. And that Nanograv website gives you information there about their PSC, which is the Pulsar Science Collaboratory. If you're trying to get, I think Tom or somebody said they're trying to get some students involved. If you're trying to get especially high school students, motivated high school students, or even college undergrads involved in pulsars, then check out that Pulsar Science Collaboratory at Green Bank. They have a great program. They train people. They have all this twice a year. They do these training classes, train these young people how to detect pulsars using data from Green Bank 20 meter, and then they turn them loose on different projects. So I haven't checked this year. I know last year they had National Science Foundation funding for that. So in fact, when I went to EADS and talked to the class down there, I tried to get some of them interested in it, but they were all busy either working or playing football or something to keep gas in their car. They didn't want to do pulsars, but many high school students really have them check out the Green Bank Pulsar Science Collaboratory. And we can work with them on that. So you select your candidate from Murmur, and that's what we're going to do here in a minute. I'll just show you what I do. You go through Murmur, select some candidate pulsars, verify with Stellarium that you're above the horizon. You don't want to go, below the horizon when you're tracking. You want to be above the horizon. You want to get an idea how long of a runtime you need. On the computer you're going to use, whether it's this one or the Raspberry Pi 5, whatever it is, I use subdirectories. So for me, I have a subdirectory by the year and the date, and then for each pulsar. So when we go down there for that day, There might be several different pulsars under a particular day, and then I can keep it organized because when you do the post processing, it can generate a lot of files, and I like keeping them separate. So you set up these separate directories, and when you go down there, each directory will need two files. One is this .par we'll talk about here in a second, and the other is a .sh. I just use bash. So this .par parameter lists some ephemeris values. It lists some timing and ephemeris values for that pulsar so that the Presto post-processing knows where to find the pulse. And if you download the database from ATNF, then you just run this command, psrcat, like it says, it shows here. And anybody that actually wants to do this, I'll be glad to help you get going on it. But you generate this .par file and just place it in the file, then Presto will pick that up. The tricky thing is, and I learned this the hard way, is some of these parameter files that are generated by ATNF are ephemeris version 5, and it's called TDC, and those are for Tempo 2. I'm not running Tempo 2. Tempo 2 is, Tempo was hard enough. Just to get Tempo installed and running was hard enough. I don't want to deal with Tempo 2 right now. And so it just means there's a few .par files we can't process. So if you do collect that pulsar, you can process it, but you're going to do it manually. You're going to have to put all the values in manually. So the .par file is just for automatic processing. So just make sure it's ephemeris version 2. And then you edit this .shell file, and I always start with a copy. You don't have to invent a new one. I'll just give you one. And the .shell file has the parameters that GNU Radio uses. Just a quick comment on this. I'm not showing any GNU Radio today. We'll look at it next time. Many of you have seen when you're looking at GNU Radio, GRC stands for GNU Radio Companion. GNU Radio Companion is your visual program. So you have these various blocks for sinks and sources and your FFTs and all the processing you're doing, all these blocks, and you just connect the dots, and that's your program. You can run that program at Haswell, and that's how Rich used to do it. I found personally that I was making lots of mistakes when I would enter in the new parameters into the GNU Radio Companion. If I mistyped something, everything is wrong. So my own preference is I prefer to script everything. So when you run GNU Radio, when you compile it, you actually generate a Python program that's callable. I call the Python program from this script where you've edited the values. So it just passes all the parameters. And for me, makes things a lot easier once you're at Haswell. You're just running this script. So before you go down to Haswell, you can initialize this script with things like the path, the name of the pulsar, the right ascension and declination, the W50, and those things that don't change. But until you actually get to Haswell on the day that you're down there, you don't know some of these other values. So the values in red, we'll talk about at the next class. How do you determine those when you get down there? The first one is the RF gain. We'll show you next time on the B210. Well, we want to be below saturation. And so you need to find the optimum RF gain. You want to find the center frequency. The center frequency is going to be, so you need to scan up and down the band for RFI for that particular day. I've seen it's different on different days. So you scan up and down the band, find the widest amount of clean frequency you can. That's your center frequency and your bandwidth. And that also helps determine the runtime. The more bandwidth, the less time you need to get an equivalent collection. And FB size is the filter bank size. So that has to do with the channel width. So I'm just kind of introducing these things today. We're going to talk about them more next time. But the FB size is something Ray and I wrestled with for some time. It took me a while to really understand it. But just think of your total bandwidth divided into channels. FB size is the number of channels. So if you have, let's say you're doing 20 megahertz of bandwidth and you do 512 channels. So that would be your FB size, be 512. So that divides that total bandwidth up into 512 channels. They're all equidistant. And a rule of thumb that I found in this handbook of pulsar astronomy, a good rule of thumb I found is um, if you're doing 14 megahertz and the dispersion measure is less than 100, you can set the FB size so that the channel width is around 500 kilohertz. If you're down at 400, which is what we're going to be doing now, for dispersion measure less than 100, then you want your channel width to be around 100 kilohertz, and so you just adjust filter bank size accordingly. Some of you have seen me when I'm down there trying to tune up the B210, and I'm sitting there scratching my head or playing around with the calculator. I'm trying to adjust some of these values on the fly. So that's part of what we do when we get there. And the more of this we can automate, the better. Now, as we'll see in Murmur also prints out the theoretical max channel width for each pulsar, so you can use that as a guide. A value that you don't have to set, it's going to be set inside the code, is the sample rate, the T-samp. And I've found works best to have the T-samp set to about 1/10 of the W50. That's the half height width of the pulse. What that means is I'm getting at least 10, when I do the analog to digital conversion, I'm getting at least 10 points on a pulse, so I can have it well defined. So the T-samp is based on the filter bank size, the bandwidth, the W50, and the Fourier frequency, the fast Fourier transform decimation rate. So there's an automatic calculation for that. And that's thanks to, oh my goodness, I'm forgetting names today. Who's the guy in Canada at CCERA?
Is that Marcus?
Yeah, Marcus. He's the one that had this code, and it was in the original code. So the history of the code is Marcus developed it, put it on GitHub, and that's where Joe Martin got it, and he simplified it, and then we got it from him. So it's kind of a hand-me-down GNU radio that we run, but Marcus was a pretty smart guy. He figured out a lot of things that we're still using. Anyway, I print those values out. When the program starts out, it prints out the channel width and T-samp, so you can look at it and think if that's in the neighborhood of what you're expecting, then you just let it go. If it isn't, you just kill it and start over. Kill it and change it and start over. And then the last slide I'm going to do today, and this is probably where we're going to start next time, is the filter bank parameters that are in the script. So this is just a little script on the Linux computer, and these all need to be set ahead of time. But by doing this ahead of time, as many as you can, I don't have to worry with the GNU Radio Companion. But you need to set the runtime in seconds, the path, the pulsar name, the right ascension and declination, and the W50. Those can all be done ahead of time. And then the day of, I just go down there, and after we've fiddled around for a while, then we set the gain, the center frequency, the sample rate, and the frequency bank size. That's the number of channels. Usually, for frequency bank size, I use either 512 or 1054, sometimes 256. Just so it's not a whole lot of numbers you need to choose from. And then you add that's all you need. Forget the bottom half of that script, because the bottom half of the script is for the post-processing. So it's just the top half that we'll need, and we'll show next time. So I'm going to switch and do demos on some of these tools. Are there any questions on the presentation slides?
Dan, is there an advantage to having a B210 to play with to try these things out?
Yes, that's absolutely critical. So I was fortunate when we started. we had the N210. The N210 is different. It's 10 megahertz bandwidth, so it's limited, but it's also Ethernet connection. And then the B210 is much better. The B210 is a USB 3 connection, and it's a lot easier to deal with, and it's much wider. And so Rick has the B210 now, but I found it critical. In fact, I spent a good couple of months when I started playing with the B210, either just hooked up to my antenna on my roof, a VHF, UHF antenna, or I'd be connected to Ray's Pulsar simulator. And that way I got used to how the B210 worked. I got used to trying to understanding these parameters. And then, because when you get to Haswell, everything's more complicated there.
Oh, yes.
So,
So
yeah.
anyone who wants to play with those, all of those are here in my lab right now. The N210, the B210, single generators, pulsar simulators, everything is right here if anybody wants to play with it.
Well, I'm
Yeah.
curious, was there a Chinese version of the B210 that
Yeah,
was
that's in
relevant?
Haswell.
Uh,
That's mine. I bought that one, and that works very well. And right now that's in Haswell, and I'm going to be swapping them. I'm going to leave the real B210 at Haswell and bring the Chinese version back here. But either way, you can always come here and play.
Okay.
So,
Yeah, because I was thinking if it's not extremely expensive, I think
It is.
the Chinese version is.
Oh, the Chinese version, if I remember, is around 750. And how
Wow.
much is the real one? 2,700 or something?
yeah,
Wow.
the real ones are like 2,700. So yeah, Rick and I, we did comparisons last year between the Chinese clone and the real one, and they were almost identical. There was not any really significant difference. They have the same chipset, so they should perform the same.
Hmm.
We have a third B210. It's the original one that was donated. It's the blue one. It's probably good enough for using in the lab,
Yeah,
but it's
I
the
have
one.
that one here also.
Yeah, so Rick's got that. That's the one that I used for a couple of years, but it just seems like the results are getting worse and worse. And then when we swapped out the coax cable and did the grounding and bonding, I also switched to the new B210 and got much better results. All those things. And what I found out was the old B210, it was getting the signal through it, but it was weaker.
Hmm.
So it may have defect in it, may be worn out. I didn't want to spend time with it, but it might be fine for just using the Pulsar simulator or lab work at home.
Hmm.
Is there a reason why you're using Stellarium over, say, Radio Eyes that has all the pulsars displayed and everything?
Uh, yeah, that's a great question. Because we do have radio eyes on our Radio Jove computer there in Haswell, and I've used it. It's a great program. I probably forgot to mention this is just one way of doing it. This is just the way I fell into doing it with the tools I had at hand. If you want to use radio eyes, that's fine. So it's really just to verify the track. Um, so that's a good point. I forgot to mention that. I'm not saying that this is the optimal way of doing things. This is just one way I found that worked. I know there's better ways of doing it. Oh, and for me, another reason was I run Linux. I don't have much Windows here, and I think Radio Eyes runs better on Windows.
I have a question. Why don't you split up the GNU radio processing into just capturing time domain IQ samples and then do all the filter bank stuff later? Just do like maximal bandwidth at the site. Does that make sense?
Oh, just collect INQ data?
Yeah, that simplifies things, and then you can do the filter bank and post processing.
Sure. Um, yeah, that's one way of doing it. In fact, we've talked about doing it that way. The INQ files are going to be huge, very large, many, dozens of gigabytes. Um, so that's another way of doing it. Um, so Stellarium you can run on almost any computer, including on your phone. And I use it for other astronomy things too, besides the pulsars. But uh, I'm not a very good astronomer because I like to sleep at night, and we can do pulsars during the daytime. And so what I do with Stellarium is I turn off the atmosphere. So this is actually looking down here. It says we're at Haswell. So I've got it set for the Haswell latitude and longitude, and it's got the current time, but I turn off the atmosphere so I can see what the sky would look like if the sun wasn't there. And so when I set it up, I might change the grid. I like to see the uh, constellations and the constellation labels so I get an idea what I'm looking at. There's a button here that says show pulsars, and all those little dots that just came up are supposed to be blue. I don't know if they are, but those are the pulsars. Then what I'll do is say, all right, I want to see a pulsar. In this case, we'll just pick our standard one. So it's almost enough to make me want to switch to radio eyes or something because the search window doesn't always want to work. And especially whenever you want to do a demo, it doesn't want to work. It doesn't accept the value. And I don't know what causes that, but so instead of looking for that one, we will look at the crab pulsar. So the crab pulsar is in the middle of the crab nebula. It's also Taurus A. It's a supernova remnant. So there's a pulsar in there. So where the blinking area is, that's the current location at the current time. This shows you where the moon is, and the sun's over here. So we like to stay 10 degrees off the sun. But then what you can do is advance the clock. So you just come over here. This shows the current day and time, and you just advance the clock. So it's 3 o'clock. You just can keep advancing the clock, and you get an idea there. The pulsar is tracking over closer to the sun, but they go at about the same rate. So the sun will set, and then that pulsar will set. So if you do this on if you do this, for example, on plus 54, it's pointing towards the north. It's circumpolar. It's up towards the north. And as you advance it, you'll see the track basically, it makes a big loop in the sky, but it's always above the horizon. I do this also on some of the pulsars, like when you look at it and it says the declination is minus 47, that's pretty low. And they only come about 5 or 10 degrees up above the horizon. They may just be above the horizon for an hour. So anyway, that's what I use. There's radio eyes. There's other tools to help you verify the track. So that's just a real quick look at Stellarium. And yeah, the only thing I've said on there is just the location for Haswell. I'm going to switch over to ATNF for a minute.
So really, to get into Stellarium, you just need to get in here and poke around in all the menus. The menus aren't really, they're kind of unusual for most of these apps.
Yeah,
And so you've got menus
there's a
along one side and up the top, and it's
yeah,
all,
and there's a lot of things you can do with it. You can almost make it into a camera. So there's a very good manual wherever you get when you download Stellarium. There's a good manual if you want to learn more about that.
Dan, you spoke of some pulsars only available for about an hour above the horizon.
Uh-huh.
Can we glue 2 days worth of observations together? That requires really stable clock capability.
Yeah, we have not tried that, but that's something that the Presto program is fine with. With Presto, and I have done multiple filter bank files just a few seconds apart. I have not tried a day apart, but you can have a gap in there. I don't know how extensive it can be, but there can be a gap, and that's what all the big sites do is they don't get an hour of dedicated time for anything. At Greenbank, you get a few minutes. But what you do is you get a few minutes every other day for a month, and then you stack it up. I need to fumble around here for a second. So this is the ATNF Pulsar catalog. It's been there for, I don't know, 20 years, and they keep it current. When somebody publishes a research paper with data on a pulsar, it bubbles up into this database, and so it usually has fairly current values. You can just think of this as a front end to a database, and you can select some parameters. You can sort them any way you want. What I usually do, I'll do something like, so name is the B name, and then J name is the J2000. If you want the right ascension and declination, you click that. So these first values are location in the sky. Then for timing, you might want the period. You can get it its frequency also. You might want the dispersion measure. W50 is the width that we use. And then let's say we're doing a collection of 400. Then I want to know what the flux is to compare. Binary only.
When it says
What's that?
P1, is that the P dot? Yeah, apparently.
Yes.
Okay.
Yeah. So each one's got a little question mark. So these are the frequencies, and that's the time derivative. So P1 is P dot. Yep. Distance parameters, we don't need the surveys. Derived parameters are interesting sometimes to look at. This is where you get the surface magnetic flux density that's calculated, or its characteristic age, and those things are all available. Like any database, you can define parameters and search it any way you want by pulsar names or whatever. I usually just do a table, and I don't like to see all the references and the errors and all that. So I say short without errors, and just give me a table. And it takes a second, and then you get this. So this is the name and the B name, J name, the period, dispersion measure, the W50 and the S400. And I can just go down. So if I'm looking for our standard pulsar is right here, 329 plus 54. It has a period of 714 milliseconds. The dispersion measure is 26.76. The W50, the width of the pulse halfway down, is 6.6 milliseconds. And its flux is 1500 millijanskis. So it's actually 1.5 janskis. It's nice and bright at 400. So this is just the database itself. And there's a variety of ways you can interact with it, including Murmur. So what I'll show here in a second is Murmur, because Murmur uses the exact same data. But if you want to download this, you just go to the same link I sent. Oh, and I'll send this presentation out because it has all these links in it. So I'll send that out to everybody. So you can download the catalog right here. The current version is 2.7.0. It's just this gzip tar file. You download it. It makes real easy. It'll make on almost anything, and then you have all this data at hand. Again, the only real reason you would need this is if you're going to be doing post-processing and you need that parameter file for automatic processing. That's how I use that. So any questions on ATNF? So we're going to take a quick look at Murmur. Murmur is a Windows executable, but I run it under Wine. And so like we showed on the slide, when you get it, you set it up, put in the Haswell, the dish lat long, and define these parameters, and then just save it. If you say save the current set as default, then that's your default settings. So I've got it set at 408 megahertz. If we're going to do 1420, I just change the frequency on it. Most of the others I just leave the same. It doesn't change the outcome a whole lot. Just if you're in the neighborhood on what your line loss is and your gain and those things, then if you know ahead of time, if you're going to do a longer collection, you can change this to 2 hours, or you can put it down to 10 seconds, whatever you want for your time, your collection. And then if you know ahead of time your integration bandwidth, which I usually don't know, but I just say, well, I hope to get 20 megahertz, maybe I'll get 30, who knows? Then you just hit the calculate button. It calculates all of these, and it gives you a little information button on them, and it gives you the formula. And almost all of these are taken from standard radio astronomy books or from that Pulsar astronomy book we mentioned. So you can verify how he calculated all these values here, noise figures. But then what we're interested in is the Pulsar results over here. So we're just seeing the pulsars that theoretically we could detect given 20 megahertz bandwidth for integration time of 1 hour, and they're sorted by signal and noise, everything above horizon. And you just click on one and it populates the values over here. The right ascension declination, the W50, the barycentric period, dispersion measure, and the flux. The estimated distance, its characteristic age, and the maximum bandwidth and expected signal to noise ratio based on an ideal world. We never get these things in reality, but it's a good relative indicator. So now the question is, well, which one do we actually want? So you click on this button saying plan observation, and it brings up a new table that's also sorted by signal to noise ratio. So the strongest ones will be at the top. Ignore these. The pulsars start here. These are supernova remnants and some other noise sources. It's got the local the local day. So today is the 23rd. Let's say you're doing this, you're planning for a weekend. Well, you can advance it up to Saturday, the 25th, and it gives you these. The numbers here from 0 to 23, that's the local hour time. These are the azimuth values. So this tells you when it's above horizon. If it's blank, that means it's below horizon. And what I've done is I've added this detection column. So if you are running this, we need to get you a copy of this little table that is the detected ones. And I just naively put in the year when it was first detected and either R or D for the initial of who was doing the collection that time. We'll have to do something a little, as we grow, we'll have to change how we get, I think it's 6 characters you get to play with in here. Anyway, this tells me at a glance, oh, I've already collected all these, either Rich or Ray or myself, we've already collected all these. We don't have to bother with them again unless we want to. But this does, at a glance, it tells you, oh, plus 54, it's up all the time. Most of the others are not. So you have to decide, well, what Ray and I noted, or at least what I noticed, is by the time we'd get to Haswell in the morning, it can take a few hours to just get the B210 set up and get it tuned on a get it tuned up for the game and do a test with your standard plus 54. It might be noon before you're actually ready to go. So sometimes we're just looking to see, well, what's available after noon. So these are the ones that are already detected. If you're trying for a new one, you can scroll down and say, well, you see one here, it's circumpolar. It's got a fairly strong signal noise ratio, but it's got a J number. Well, that tells me that it's probably a millisecond pulsar. And so it's J2238. So then I go back to this table, to the main panel, and look at that one, J2238, and come over here and see the period. Oh my goodness, it's 3 seconds. Yeah, that's a really slow one. But it's bright, so that might be one to try. I don't recall trying that one before. A number of these Ray and I have tried over the years, but there's many of them that we did not get. We were trying to not get them. So many of these we've tried, but I don't remember trying this one. But while 3 seconds to you and me may not be much for the software, when it's trying to find something at 3 milliseconds, it does not do as well up at 3 seconds. But that would be one to try for maybe a 30-minute collection or something. You may have a favorite pulsar that you'd like to detect. Unfortunately, I have not found a way of searching this table. It's in ordered by signal to noise ratio, and you just kind of scroll down looking for a pulsar. And the one I want to look for is this one, B1919 plus 21. So that was the first pulsar ever detected by Jocelyn Bell. She was in England doing a doctoral research, and she detected the first one with this large antenna array scattered across the farm field. I think it was at 88 megahertz. So it's pretty low in frequency. And for us, there's a lot of noise down that low at 88 megahertz. But that was the very first one detected. We have not detected that as not for not trying. We have tried several times. Unfortunately, when I tried that one, I was at the wrong frequency. Let's see. So 1919 plus 21. If I come back to murmur, I go down and find 1919 plus 21.
On your system parameter, it says that the line loss after the LNA is 4 dBs. Is that real calculated or guesswork?
Guesswork. And I don't think it's that critical. You can change these numbers and it doesn't change the outcome a whole lot. I'm just trying to get relative values. So, yeah, some of these values might be suspect. Some of them are a little bit close, but Ray and I have talked about them, and
Yeah, we can calculate that one based on the line loss for the coax type and the frequency we're running.
yeah.
So, you know, you can get pretty close on that if you really want to. But that's probably a pretty good number, about 5 dB.
So what I do, I don't see the one I'm looking for. What you can do is one is changes to all of them. So instead of just showing me what's above the horizon, it's now showing all of them. And then I say sort by name instead of by signal noise ratio. Now I can go down and find this one I'm looking for, the B1919 plus 21.
And can you set up a different horizon instead of 0 elevation, maybe a 15-degree elevation, depending on your site?
You know, I haven't tried that. I don't think so. Let's see. If you want to set the observation location, here's where I set it up for Plissner. It takes the latitude and longitude, but I don't see any kind of an offset or a buffer in this, so that you can't do it there. You might just change your, I don't know. That's a good question. I've never had to deal with that because we don't have anything down there. We go from horizon to horizon. So I sorted by name and said, give me all of them. So it's 1919 plus 21. Then I come over here and see, so this is again Jocelyn Bell's. It has a period of 1.3 seconds, the dispersion measure of 12, the flux at 400 is 57 millijanskis, and that's reasonable. We should be able to do that. I remember last time I went down there, for some reason, I probably spent an hour tracking this pulsar thinking we could get it, not realizing we were at 1400, and that's right at the lowest we've ever done is 19 millijanskis, so it's kind of a wasted time there. So this one drops off sharply. They don't all go, it's not linear. It's not a linear change between the 400 and the 1400 flux, so it's handy to look at the table. This one drops off sharply. It's much, much stronger down at 88 megahertz where she first detected it, but we could do it at 400. And it's, yeah, so that one's reasonable. So I go back over here and I see, okay, so 1919 plus 21, it's up until 1 o'clock. So if we're going to do it, we get there early. If we're going to do it this time of year, it depends on the time of year, but we're going to do it now. We'd want to get there early and get set up and tested so that probably by 9 or 10 o'clock, you're actually collecting live data on that particular one. And then what I'll do is I'll jump back to Stellarium and look at the same pulsar, 1919 plus 21, just to verify that it's still, like 5 degrees above the horizon at 1 o'clock or whenever it's set, just so I know how much time I'd have to run it. But those are just, and there's other ways of using this tool. You can use it to track noise sources and calculate the you can do the noise factor with the Y method and things like that. I haven't bothered with those because I just want to know where the pulsar is and some of these parameters. Any other questions on murmur? Oh, and if you do want to install it, I don't know why, but it's hard to download it from the website. Rick has it, and just ask him for the link because it's I don't know why their website doesn't work good to download it.
The link to his website is in the email I sent out to the
Okay,
entire club.
yeah.
At
Anyway,
at the
yeah,
bottom of the plan observation, it says save horizon. What is that?
oh, here? I don't know. Never used it. Oh, so yeah, those are good questions. And the author, the ham is I0 NAA in Italy. He's put together, I don't know, it's about a 20 or 30 page presentation, an introduction on how to use this. And he gave it at a Sarah conference. So we have that. If somebody wants that, I think Rick has it or I have it, or we can post it up on our website. But if you really want to start using Murmur and explore these other options that I never use, then you really want to look at his.
I think that's what I was talking about. At 0 to 30 degrees, you can put a number like 10 degrees. 30 to 60, you can put 5 degrees, whatever, and just down the line, and you can save your horizon. That's got to be it.
Okay, sure. Yeah, you're right. I never thought about that. I never looked at it because I didn't need it. But if that's something you need, there it is.
Yeah.
Hey, Dan, before you leave that, how did you get the plan observation window to come up?
So that's this button right here.
Oh, okay, I got it.
And there's other buttons to push. You can push the show all list, and it gives you all of the pulsars. And in fact, this is the same data that you'd see in the ATNF database. It's just ordered differently, and it's not everything in it. But that's the ATNF there.
Okay.
That's all of them that you might see at 408. So